In this video, we'll see how to perform deletion in a heap tree. Now we can delete any node from the tree, but the deletion of root node is useful as it gives us the largest value of the heap. Now suppose we have to delete the root node from a heap of size n. So first the key in the root node is stored in some variable, and then the key in the last leaf node is copied to the root node. That is, key at index n is copied to index 1 because the root is stored at index 1 and the last leaf node is stored at index n. After this, the size of heap is decreased to n minus 1, and then we call restore down procedure for key in the root node because this key might violate the heap order property now. In this restore down procedure, the key is moved down in the tree and placed at its proper place. Now let's see what this restore down procedure is. Suppose k is the key that is violating the heap order property. So we have to perform restore down for key k. We compare k with both its left child and right child. We can have three cases: when both children are smaller than k, when one child is greater than k, and when both children are greater than k. Now in this case, the heap order property is satisfied, so there is nothing to be done. In this case, the greater child is moved up. So if left child is greater than k, left child is moved up, or if right child is greater than k, then the right child is moved up. Now in this case, if both children are greater than k, then the larger of the two children is moved up. Now in these two cases, we try to insert the key k in place of the child that is moved up. And we try to do this insertion by following the same procedure of comparing with both children and moving the child up. This procedure stops when both children are smaller than k or when we reach a leaf node. Now let's understand this with the help of examples. We have to delete root from this heap of size 13. So first the key in the root node is assigned to a variable, and then the key in the last leaf node is copied to the root node. So this 32 is copied here. Now the size of heap is decreased, it becomes 12. So this is not a part of heap now. Now we have to perform restore down procedure for this key. We compare this key with both its children. Both the children are bigger, so we'll move the bigger one up and we'll try to insert this key here. Now again, we'll compare this key with both the children. This one is bigger, so we'll move this up and we'll try to insert 32 here. Now again, we compare this key with both children. Now both children are smaller, so heap order property is satisfied and we can insert the key here. Now let's take another example. We have to delete root from this heap of size 13. So first the key in the root node is assigned to this variable. Then key in the last leaf node is copied here. Then the size of heap is decreased. So this is not a part of heap now. Now we have to perform restore down for this key in the root node. So we compare this key with the keys of children. Both the keys are bigger. So the bigger one of the two is moved up and we try to insert 15 here. Now again we compare with both children. This one is bigger, so we move 42 up and we try to insert 15 here. Now we compare this with this child. This is bigger, so we move it up here and we try to insert 15 here. Now we have reached a leaf node, so we have to insert 15 here. Now let's see the runtime complexity of deleting the root node. In restore down procedure, we have to move on a single path from root node to a leaf node. So if h is the height of the tree, then the runtime complexity becomes order of h. And we know that the height of a complete binary tree is ceiling of log base to n plus 1. So this becomes order of log n. Now we'll see the function for deletion. This is the method delete root that deletes the root from the heap tree. This method will return the key present in the root node. Now, if the heap size is 0, then we throw this exception that we have defined here. Now first the key value in the root node is assigned to this variable max value. Then the key value in the last leaf node is copied to the root node. After this, heap size is decremented and then we call this procedure restore down for the key in the root node. And at the end, the value of this variable max value is returned from this method. Now let's see this method restore down. Here I is the index of the key that is violating the heap order property. Here the root key was violating the heap order property. And index of root key is 1. So we have sent 1 here as argument to this method. Now k equal to ai. So k is a key that has to be moved down in the tree. First we are calculating the index of the L child and R child of this key k. Now inside this while loop we are comparing this key k with both left child and right child. If this key k is bigger than the keys in both left child and right child, then this key k is placed at the ith location and we'll just return. Otherwise, if the key in the left child is greater than the key in the right child, then the key in left child is moved up and we'll try to insert the key k in the place of left child. So this I becomes equal to L child. Otherwise, the key in the right child is moved up and we try to insert key k in the place of right child. So this I becomes equal to R child. In each iteration of this while loop, we are updating the values of L child and R child. And this loop will terminate when this value of R child becomes greater than n. Now, if the number of nodes is even, we have to place a separate condition here. Let's see why. If the number of nodes is odd, then all the nodes are either leaf nodes or have 2 children. If the number of nodes is even, then there is a node that does not have a right child. This does not have a right child here. This does not have a right child here. It has only a left child. And the index of this left child is n. We could not check for this left child in our while loop. So we have to place a separate condition for this left child. So this is the special condition that we put for the left child. Now at the end, this key k is placed at the ith location of the list. Now this is the code where we have tested the insert and delete methods of our heap class. Here we have called this method insert, and here we have called this method delete root, and here we have called this method display. Now let's run this program. Now let's display this heap. Heap size is 7 and this is the list that represents the heap. Now let's delete root. This 99 is deleted. Again we'll delete. 96 is deleted. Again we delete. Now let's display. So now the heap size is 4 and this is the list that represents the heap.